So here we are going to see the thermal conductivity of insulating powder. So before going to the experiment, so let us discuss what is meant by this insulating material. So here we are going to have different materials like asbestos, glass wool. So these are all known as insulating materials. So which restricts the heat. So that's why we are going to call this as the insulating materials. So here we are going to use the conduction. So coming to the governing law for conduction is Fourier law of heat conduction. So Q is equal to minus Ka dt by dx. So coming to this experimental setup. So here you can see these are the two concentric spheres we are going to use. So in between that two concentric spheres, we are going to place the insulating powder. So in between two concentric spheres, we are going to place the insulating powder, and we are going to calculate the thermal conductivity of that insulating powder. So obviously, that insulating powder will have less thermal conductivity, right? Because it acts as an insulating material. So coming to the experimental setup, so here you can see this is the voltmeter reading and this is the ammeter reading, and here you can see this is the temperature indicator. So now we are going to turn on this switch and we are going to supply heat to the inner sphere. So we are going to adjust this voltmeter reading as well as ammeter reading to heat the inner sphere. So this we are going to turn on this knob and we are going to adjust the voltmeter reading as well as ammeter reading. So now we are going to make 50 watts to the inner sphere, so the voltmeter reading will be 110 and ammeter reading will be 0.5. So approximately, so the voltmeter reading we are going to adjust to 110 and this ammeter reading to 0.5, so that we are going to supply 50 watts of power to the inner sphere. So Q is equal to V into I. This gives us the amount of heat we are going to supply to the inner sphere, right? Now coming to this thermocouples position. So T1, so total we are going to use 12 thermocouples here. So T1 to T6 we are going to place on the inner sphere, and from T7 to T12 we are going to place on the outer sphere, right? So in order to get the inner sphere average temperature, we are going to make the average from T1 to T6. And in order to get the average temperature of outer sphere, we are going to make the average of T7 to T12. So that we are going to get the inner temperatures and outer sphere temperatures. So now coming to the calculation part, so we are going to use the equation Q is equal to delta T by R, right? So here R is known as the thermal resistance. So what is the thermal resistance for sphere? So R is equal to 4 pi K Ri R naught divided by R naught minus Ri, outer radius minus inner radius. So that is the thermal resistance for the sphere. So now Q is known to us. So what is the Q here? So 50 watts is equal to delta T. So that is the inner temperature inner temperature minus outer temperature divided by 4 pi K Ri R naught. So radius is known to us, inside radius and outside radius. So from that we can calculate the thermal conductivity of insulating powder. So by doing this experiment, we are going to calculate the K value, thermal conductivity of this insulating powder. So remember that we are going to place the insulating powder in between two concentric spheres. So one is inner sphere and outer sphere. In between that inner and outer, we are going to place the insulating powder, and we are going to calculate the thermal conductivity of that insulating powder.